The universe is going to die, not in an explosion, not in a collapse, not in any dramatic finale that makes for a good last image, just quietly, over a stretch of time so incomprehensibly extended that every word we normally use to describe long durations, years, centuries, millennia, eons, in the ordinary sense becomes completely useless before we even get to the interesting part. The last star will go dark. The last black hole will slowly, particle by particle, evaporate into the void. And then there will be nothing. Not nothing the way a darkroom is nothing. Something far more total than that. A universe without structure, without energy gradients, without any difference between one region of space and another. A universe in which nothing can ever happen again, because happening requires a difference, and all differences will have been erased. This is what physicists call heat death, and for most of the 20th century, it was considered the clean, final, mathematically rigorous answer to the question of what happens at the end of everything. Not a guess, not a philosophical position, a conclusion that follows directly from the laws of thermodynamics, applied to the longest possible timescales. Then, a Nobel Prize-winning physicist looked at that silence and said, "Wait, because that silence, that perfect, featureless, maximally disordered final state of the universe, is not an ending at all. It is mathematically and geometrically and, if the argument holds, physically indistinguishable from a beginning. The heat death of our universe may be, from the right mathematical angle, identical to the Big Bang of the next." His name is Roger Penrose. He is 94 years old, one of the most decorated theoretical physicists alive, and one of the very few people in the world who has made a career of finding things that everyone assumed were settled and showing that they were not. The theory he built around this observation is called conformal cyclic cosmology. It is not a fringe idea. It is not metaphysics dressed in equations. It is a mathematically precise framework built on tools that physicists have used for decades, and it makes a specific, quantifiable, testable prediction about patterns in the oldest light in the observable universe. Whether it is correct is genuinely unknown. Whether it is falsifiable is not in question, and whether it is worth understanding is settled the moment you realize what it is actually saying. It is saying that the radiation passing through your body right now, the faint microwave glow that fills every cubic centimeter of space in the universe, may carry within it the compressed afterglow of a cosmos that lived and died before ours was born. That is what we are here to understand tonight. Get comfortable. This is going to take a while, and the timescales involved are going to make everything you thought you knew about the word long feel embarrassingly inadequate. To appreciate what Penrose is proposing, you first need to feel the full weight of what the standard picture of the universe's future actually looks like. Not a summary, not a sketch, the real thing, with the real numbers. The framework that most cosmologists use for thinking about the far future of the universe was laid out in detail by astrophysicists Fred Adams and Gregory Laughlin, whose 1999 book, The 5 Ages of the Universe, organized cosmic time into 5 broad chapters. It remains one of the clearest maps we have for what physics actually predicts will happen between now and the end of everything. We are currently living inside the second of those 5 chapters, the Stelliferous era, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited in the darkness of the early cosmos, and it will end somewhere around 100 trillion years from now, when the last of the universe's long-burning fuel is exhausted. 100 trillion years written out. That is a 1 followed by 14 zeros. It sounds enormous, and relative to any human timescale, it is, but in the full context of what comes after, the Stelliferous era, the entire era of stars. All the galaxies and supernovas and planetary systems and everything that has ever happened that we would recognize as cosmically interesting is actually a brief opening chapter. The real story starts when it ends. Here is why. Stars form when gravity compresses clouds of hydrogen and helium gas until the pressure and temperature at the center become high enough to ignite nuclear fusion. Fusion pushes back against gravity, and this balance, gravity pulling in, fusion pushing out, is what defines the active life of a star. But the fuel is finite. Every star is slowly converting its hydrogen into helium and eventually into heavier elements. And when the fuel runs out, the balance breaks. What happens next depends on the star's mass. Stars like our Sun end their active lives by expanding into red giants, shedding their outer layers and leaving behind a dense, slowly cooling remnant called a white dwarf. More massive stars end in supernovas, leaving neutron stars or black holes. The smallest stars, the red dwarfs, the dim and miserly ones, burn so slowly and so efficiently that a red dwarf, with a fraction of the Sun's mass, can sustain fusion for trillions of years on its own. But even the most fuel-efficient stars eventually exhaust their hydrogen. By around 100 trillion years from now, the last active red dwarf will flicker and fade. Star formation itself will have ended long before that, because the molecular cloud material that gravity compresses into new stars will have been used up or dispersed. No new ignitions, no new light. The stelliferous era ends in darkness. What follows is what Adams and Lachlan called the degenerate era. The universe is now populated entirely with stellar remnants, white dwarfs, cooling toward absolute zero across timescales measured in quadrillions of years, neutron stars, spinning down brown dwarfs, the objects that never quite had enough mass to ignite, and black holes, growing fat on anything that wanders close enough to be captured. The universe is dark, cold, and vast, but it is still structured. There is still matter. There is still gravity organizing things. The game is not yet over, but here is where the physics gets uncertain in an important way. The standard model of particle physics predicts that protons are stable. It contains no mechanism for proton decay. But nearly every extension of the standard model, every grand unified theory that attempts to bring the strong nuclear force into alignment with the electroweak interaction, predicts that protons do eventually decay. On timescales, somewhere around 10 to the power of 30, 4 to 10 to the power of 40 years, we have been searching for proton decay in enormous underground detectors for decades, watching vast tanks of water for the faint flash of light that a decaying proton would produce, and we have found nothing. The experiments keep pushing the lower limit on the proton's lifetime higher. Whether protons decay at all remains one of the genuinely unresolved questions in particle physics. The answer matters enormously for the far future. If protons do decay, then all ordinary matter, every atom that has not been swallowed by a black hole, will dissolve into radiation, and lighter particles somewhere around 10 to the power of 40 years from now. White dwarfs, neutron stars, planets, every solid object in the universe will come apart at the particle level, leaving behind nothing but a diffuse bath of electrons, positrons, and photons. If protons do not decay, then some of these objects persist essentially indefinitely, though they still lose mass over even longer timescales through quantum tunneling processes that slowly rearrange their constituent particles. Either way, by the time we reach the black hole era, which Adams and Lachlan define as beginning around 10 to the power of 40 years and lasting until approximately 10 to the power of 100 years, the universe contains essentially nothing but black holes of various masses. No stars, no planets, no ordinary matter in any recognizable form, just black holes, scattered across a universe that has been expanding for so long and at such an accelerating rate that the distances between any two black holes are effectively infinite for any practical purpose. And then there are the black holes. Stephen Hawking showed in 1974 that black holes are not permanent. They radiate. Not quickly, not in any way that would be detectable for stellar mass. Black holes given the technology or even the physics of our current universe. But measurably, in principle, the mechanism involves the strange behavior of quantum fields near the event horizon. The quantum vacuum is never truly empty. Pairs of virtual particles flicker constantly into existence and annihilate each other, too brief to be directly observed. Near the event horizon of a black hole, one particle of such a pair can fall inside the horizon while the other escapes. The escaping particle becomes real, carrying energy away from the vicinity of the black hole. The energy ultimately comes from the black hole's own mass. The result is that black holes very slowly evaporate. For a stellar mass black hole, one produced by the collapse of a massive star, perhaps 10 times the mass of our Sun, the evaporation time is approximately 10 to the power of 67 years. That is a number with 68 digits. The current age of the universe is roughly 13.8 billion years, which is approximately 10 to the power of 10 years. The evaporation time of a single stellar mass black hole makes the entire current age of the universe look like a rounding error. For the supermassive black holes that sit at the centers of galaxies, objects like the one at the center of the Milky Way, Sagittarius A star, which has a mass of about 4 million solar masses, or the monster at the center of the galaxy M87, which tips the scales at 6.5 billion solar masses, the evaporation time extends to approximately 10 to the power of 100 years. That number has a name, a googol, a 1 followed by 100 zeros, 10 to the power of 100 years. The current age of the universe, scaled to this number, is smaller than a single heartbeat is to the age of the universe. We are not talking about a longer time scale in the normal sense. The exponent itself is 90 times larger than the exponent describing the current age of the universe. The difference in scale makes every metaphor fail. As a black hole evaporates, it loses mass. As it loses mass, its temperature rises. Black holes are counterintuitively hotter when they are smaller, because the relationship between mass and temperature in Hawking radiation is inverse. A more massive black hole radiates at a lower temperature. A smaller black hole radiates at a higher temperature. As a black hole shrinks, it radiates more intensely, losing mass faster, which makes it hotter, which makes it radiate faster still. The process accelerates toward the end, culminating in a final burst of high-energy radiation as the last fraction of the black hole's mass is converted into photons, neutrinos, and lighter particles, and then the last black hole finishes evaporating, and the universe is left with precisely nothing but a faint, incredibly dilute, incredibly cold bath of photons, neutrinos, and gravitons, expanding outward through a space that has no structure, no complexity, no gradients, no events. This is heat death, maximum entropy, the final state. The equations of physics still technically apply. Space-time still exists. In some sense, expansion continues, but nothing changes, because change requires energy to flow from somewhere to somewhere, and all the somewheres have equal. This is supposed to be the end. For most of the 20th century, it was. Then Roger Penrose looked at it from a different angle. Heat death as an ending has a philosophical problem embedded in it. And most physics courses skip past this problem because it does not have a clean resolution and it is uncomfortable to dwell on. The problem is this: heat death is not the universe disappearing. It is the universe persisting forever in a state in which nothing can happen. The equations keep running. Space-time keeps expanding. The bath of photons keeps drifting outward. But no process of any kind can occur, because every process requires an energy gradient, a difference between here and there, between hot and cold, between ordered and disordered. And heat death is precisely the elimination of all such gradients, permanently. So the universe does not end. It simply becomes, for all physical and practical purposes, dead, while technically continuing. And the word forever in this context means an actual forever, not a very long time, but infinite duration. Infinite duration of absolutely nothing happening, in an expanding space so vast that no photon will ever traverse the distance between any two of the sparse particles still wandering through it. If you find that deeply unsatisfying, you are in excellent company. Physicists have been quietly uncomfortable with it for a long time, but the unease goes deeper than aesthetics. There is a fundamental logical tension sitting inside the standard cosmological picture that the heat-death scenario throws into sharp relief. The universe did not start in a random state. It started in a state that was, by any rigorous thermodynamic accounting, extraordinarily improbable, almost impossibly ordered, and a physics that can tell you with great precision what happens next, but cannot explain why the story started the way it did, has a significant gap in its foundations. Consider the thermodynamic arrow of time. The reason your coffee cools and does not spontaneously reheat. The reason eggs break but do not reassemble themselves. The reason the past is different from the future in all ordinary experience. All of this exists because entropy increases. And entropy increases because the universe began in a state of low entropy. The direction of time, the reason causes precede effects, rather than the other way around, is entirely a consequence of the special, ordered initial condition of the universe. Without that initial condition, there is no arrow of time. There is no before and after. There is just a timeless equilibrium. So the question that heat death, stretched to infinity, throws into sharp relief is this: if the universe is heading toward maximum entropy, and if maximum entropy is the natural, overwhelmingly probable state for any physical system, then why on earth did the universe begin in the opposite state? Why did the Big Bang start from a configuration of such extraordinary, almost impossibly precise order? Standard cosmology does not have a satisfying answer to this. Cosmic inflation, the rapid, exponential expansion of the very early universe that most cosmologists accept as explaining the smoothness of the cosmic microwave background, does an extraordinary job of accounting for many features of the universe we observe today. The flatness of space, the uniformity of the microwave background, the specific spectrum of density fluctuations that seeded the formation of galaxies and galaxy clusters. Inflation explains all of this with remarkable precision. But inflation does not explain why the pre-inflationary state had the precise properties needed to produce the inflation we observe. It does not answer the question of what selected the initial conditions. You still need an extraordinarily special starting configuration to produce the universe inflation describes. The problem has been shifted, not solved. Roger Penrose made this argument concrete and quantitative in a way that is very difficult to ignore once you have seen it. He calculated the probability that the Big Bang started in the configuration it actually started in compared to all other possible configurations of the same total energy. The result was a number that is almost impossible to write down, let alone grasp. The probability, in Penrose's calculation, is approximately 1 in 10 to the power of 10 to the power of 123. That is not 10 to the power of 123. That is 10 raised to the power of 10 raised to the power of 123. The number of zeros in the exponent has more than 100 digits. If you try to write this probability as a decimal fraction, the number of zeros before the first non-zero digit would itself be a number too large to write down in the observable universe. There is no analogy that makes this intuitive. It is simply beyond the range of anything that has physical meaning as a description of luck or coincidence. The Big Bang did not start the way it did because the universe got lucky. Something about the physics selects that initial condition, and standard cosmology has no convincing account of what that something is. This is the problem Penrose set out to solve, and the solution he proposed involves looking at the end of the universe and recognizing something in the mathematics of that ending that the rest of the physics community had overlooked. Before going further into the theory, it is worth spending a proper amount of time on who Roger Penrose is and why his intuitions about the deep geometry of the cosmos have historically been worth taking seriously, even when they initially seem eccentric. Penrose was born in 1931 in Colchester, England, into a family that included a distinguished geneticist father and an accomplished artist mother. A combination that perhaps explains something about the way he thinks, which has always been unusually geometric, unusually visual, unusually focused on the structural relationships between things rather than on computation alone. In the 1960s, working with Stephen Hawking, Penrose proved mathematically that the formation of black holes is an unavoidable consequence of Einstein's general theory of relativity. His singularity theorems established that once a massive enough object begins gravitational collapse, no physical force or process can stop it from forming a singularity, a point of infinite density, where the equations of general relativity break down entirely. This was not a hypothesis or a conjecture, it was a proof. It followed directly from the geometry of spacetime, as Einstein described it, under very general assumptions about the behavior of matter. It changed how physics understood both black holes and the Big Bang, since the same theorems that apply to collapsing stars also apply, run backward in time, to the expanding universe we observe today. Decades later, in 2020, Penrose was awarded the Nobel Prize in Physics for this work. He was 90 years old when the prize was announced. The committee was not honoring speculation. They were honoring mathematics that had shaped the foundations of theoretical physics for 60 years. Penrose also developed twistor theory, an alternative mathematical framework for quantum gravity that reformulates spacetime in terms of the geometry of light rays rather than of points, and which has been influential in mathematical physics for decades beyond its original motivation. He wrote a 1,200-page book called The Road to Reality, which is a tour of the mathematical underpinnings of modern physics, considered one of the most rigorous popular science texts ever attempted. He has made important contributions to tiling theory, to the mathematical understanding of consciousness, and to the geometry of spacetime in ways that continue to generate research decades after the original papers. The point of all this is not credential worship, it is context. When Penrose proposes something unconventional, the appropriate response is not to dismiss it because it sounds strange. The appropriate response is to examine the mathematics carefully, because his geometric intuitions have a documented history of being correct in exactly the situations where they initially appeared most counterintuitive. His intuition here is this: the problem of the Big Bang's extraordinarily special initial conditions is not a coincidence to be explained away. It is a clue. It is pointing towards something about the relationship between the end of a universe and the beginning of the next one. And the mathematical language required to see that relationship is not new physics. It is geometry that already exists in the toolkit of general relativity, waiting to be applied to the right question. The theory he built from this intuition, first laid out fully in his 2010 book Cycles of Time, is called conformal cyclic cosmology, and the key word, conformal, is the one we need to understand before any of the rest of it makes sense. There is a fact about photons, particles of light, that special relativity tells us with complete mathematical precision, and which most people have heard, stated in the abstract, but have never really sat with long enough to feel the full weight of it. Photons do not experience time differently from us, not experience time at a slower rate, the way a moving clock does in special relativity, or the way a clock near a massive object runs slow relative to a distant observer. Photons traveling at the speed of light through a vacuum have zero proper time elapsed between any two events on their trajectory. From the precise mathematical standpoint of special relativity, a photon emitted at the Big Bang 13.8 billion years ago and detected by your eye tonight has experienced exactly no elapsed time between emission and detection. Not a little time, zero time. The entire history of the universe, from our perspective, occupies no duration whatsoever from the reference frame of a particle traveling at the speed of light. This is not a metaphor or a loose philosophical claim. It follows directly from the definition of proper time in special relativity. Proper time is the time recorded by a clock that travels with an object, the time on a watch strapped to that object's wrist, regardless of how the object is moving relative to any external observer. For massive objects moving at speeds less than the speed of light, proper time is always positive, always accumulating, always advancing. But the formula for proper time includes a term that depends on velocity relative to the speed of light, and at exactly the speed of light, that term goes to zero. Proper time stops accruing entirely. The photon's internal clock, if it had one, would show the same reading at emission as at detection, regardless of how many billions of years separated those events in our reference frame. This means photons carry no internal timekeepers. They cannot, in any meaningful physical sense, experience duration. A photon does not age. A photon does not tick. A photon travels from one event to another, with no elapsed time in between. Now hold that fact, and ask, why does it matter for a theory about the end of the universe? It matters because of what the universe is made of in its far future. After all, the black holes have evaporated. After every massive particle has either decayed, or been absorbed, or annihilated. The universe consists almost entirely of photons, radiation, particles of light, moving at the speed of light, which by definition experience zero proper time, which means the universe in its final state has lost all its internal timekeepers. The clocks are gone, not misplaced, not broken, but physically, thermodynamically, irreversibly absent. The only things left are entities that physics describes as experiencing no elapsed proper time between events. If you want to define time in the physical, operational sense, not just as a coordinate in an equation, but as something that can actually be measured, that a physical system can actually track, you need a clock. And a clock requires a massive object moving along what relativists call a time-like trajectory through space-time. It requires something that accumulates proper time, that can compare the reading at one moment to the reading at another. A universe made entirely of radiation, entirely of photons and other massless particles, has, by the fundamental rules of special relativity, no capacity to measure time at all. This is the first crack in the wall of heat death, as a final ending, not a philosophical objection, a physical one. The far future universe has no clocks, and here is where something remarkable appears. If you look carefully, the very early universe, the first tiny fractions of a second after the Big Bang, when temperatures were so extreme that the energy scale vastly exceeded the mass of any particle, was also, in an important physical sense, without clocks. The temperatures were so high that every particle's thermal energy was enormous compared to its rest mass. In that limit, mass becomes irrelevant to the dynamics. Particles behave as if they were massless. The physics approaches the regime that physicists call conformal invariance, a condition in which the equations of motion are unchanged when you rescale all distances and times by the same factor. Two universes without clocks, one at the beginning of the story and one at the end. And Penrose's insight is that if the physics at both ends is structurally the same, if both are dominated by radiation, both are approximately timeless, both exist in a regime where mass plays no role, then maybe these two endpoints are not as different as they appear. Maybe in the precise geometric language of conformal transformations, they are the same kind of object. Maybe the infinite future of one universe and the initial singularity of the next share a mathematical structure that allows them to be identified with each other. But to understand what that identification actually means, we need to understand what happens to the concept of scale when all the clocks are gone. Let us think very carefully about what it means, physically, to measure size. If you want to say that an object is 1 meter across, you need a reference. Something defines what a meter is. In practice, the definition of the meter in modern physics ultimately traces back to the speed of light and the duration of a certain number of oscillations of a cesium atom. In other words, it requires a clock. Without a clock, without a physical process that repeats at a definite rate and can be counted, the operational definition of any length unit breaks down. You can still write the symbol for a meter in an equation, but it no longer refers to anything physically real that a measurement inside the universe could access. This is not an abstract philosophical point. It has specific physical content that matters enormously for what happens at the far future of the universe. Imagine two universes. In the first, every distance, every wavelength of radiation, every physical length has been multiplied by a factor of 1 billion compared to the second. The distances between all particles are 1 billion times larger. The wavelengths of every photon are 1 billion times longer. Every length is uniformly scaled up. Now ask, is there any physical measurement you could perform inside one of these universes that would tell you which one you are in? For a universe containing massive objects, the answer is yes. A massive particle has a Compton wavelength, a quantum mechanical length scale set by the relationship between the particle's mass, the speed of light, and Planck's constant. The electron, for example, has a fixed mass and therefore a fixed Compton wavelength. If you compare that wavelength to the size of some other structure in the universe, you get a dimensionless number that is different in the two universes. Mass gives you an absolute scale reference. Mass is, in a deep sense, what makes the concept of size physically meaningful. But in a universe with no massive particles, a universe that contains only photons, there is no Compton wavelength. There is no fixed length scale that persists independently of the overall scaling of everything. Every length scales together when you apply a conformal transformation, and the physics is unchanged. The two universes, the large one and the small one, are for all physical purposes identical. No experiment conducted inside either one could distinguish them. This is what conformal invariance means in concrete physical terms. and Penrose's claim is that this is precisely the state the far future universe reaches, a state where scale, in the physical sense, has become meaningless, where there is no measurement you could perform that would tell you how big the universe is, because there is nothing available to define what big means, and the early universe was in a similar state, though reached through a different mechanism, not because everything has cooled and decayed, but because the temperatures were so extreme that the masses of particles were irrelevant compared to their thermal energies. In the first instance after the Big Bang, the physics was approximately scale invariant for the same mathematical reason. Mass played no significant role, and without mass, you have no absolute scale reference. The far future is conformally invariant because everything has cooled and all massive particles have decayed or annihilated. The early universe is approximately conformally invariant because everything is so hot that mass is irrelevant. Different mechanisms, same mathematical property, and here is the heart of Penrose's observation. Conformal invariance is exactly the property you need for a specific geometric operation, the operation of mapping an infinite future onto a finite boundary, of taking a universe that expands forever and compressing it into a surface, a conformal boundary that can then be identified with the initial surface of a new universe. And if both the end and the beginning shared this conformal invariance, then that identification is mathematically coherent. The end of one universe becomes, under the right conformal frame, the beginning of the next. But the mathematics of how this actually works requires a precise formulation, and the person who provided that formulation was not Penrose alone. Paul Todd is a mathematician at Oxford who has spent decades working on the geometry of spacetime at its boundaries and extremes. In the context of conformal cyclic cosmology, he is responsible for turning Penrose's physical intuition into a mathematically rigorous proposal. The problem Todd addressed is fundamental. The Big Bang singularity in standard general relativity is a place where the curvature of spacetime becomes infinite, where the equations break down, where physics as currently formulated cannot say anything meaningful about what happened. It is, in the language of differential geometry, a genuine singularity, a point at which the mathematical machinery of the theory fails entirely. Penrose himself proved, with his singularity theorems, that such breakdowns are inevitable consequences of general relativity. The Big Bang is one of them. This has always been understood as a fundamental limitation of the theory. We cannot describe what happened at or before the Big Bang, because general relativity simply stops working there. But Todd pointed out something subtle and crucial. Not all singularities in general relativity are the same kind of thing. Some are genuine physical breakdowns, where curvature diverges in ways that cannot be resolved without new physics. Others are what mathematicians call conformal singularities, places where the equations appear to break down not because the physics is truly singular, but because of the coordinate system being used. Switch to a different mathematical frame, and the apparent singularity disappears, revealing a perfectly smooth surface that the theory can be extended through without any difficulty. The classic example of this is the event horizon of a black hole in certain coordinate systems. In the coordinates that Schwarzschild originally used to describe the geometry around a black hole, the event horizon appears as a singularity. But if you transform to different coordinates that an infalling observer would naturally use, the singularity vanishes completely. The event horizon, in the right frame, is a perfectly ordinary surface. Physics can be extended through it in both directions. Todd's insight was that the Big Bang singularity might be this second type, that if you strip away the scale information, If you look at the space-time geometry of the Big Bang purely in terms of its conformal structure, its angles and causal relationships rather than its distances and absolute sizes, the singularity might not be a genuine breakdown at all. It might be a smooth, conformal boundary, a surface that space-time can be extended through mathematically if you work in the right conformal frame. The technical tool that makes this precise is called conformal compactification. The idea is to take a space-time that extends to infinity in some direction, either infinitely far into the future or back to a zero scale, past, and apply a conformal transformation that maps the infinitely extended region into a finite one. The transformation squashes infinity into a boundary. The infinite future of the universe becomes a finite surface in a reschooled geometry. The initial singularity of the Big Bang, run backward, becomes a finite conformal boundary in the distant past. In the visual representations of spacetime that Penrose himself developed, the so-called Penrose diagrams, this appears as a diagonal line or surface at the edge of the diagram, representing all of infinite future or the initial singularity compressed into a geometric edge you can draw on a page. What Todd showed is that if Penrose's whale curvature hypothesis is correct, if the Big Bang really did begin with a specific component of spacetime curvature, the whale tensor, equal to zero or very close to it, then the initial conformal boundary of our universe is a smooth surface rather than a genuine singularity. And if the far future of the previous eon was in a conformally invariant, radiation-dominated state, then its future conformal boundary is also smooth. Smooth surfaces can be identified with each other. The future conformal boundary of the previous eon becomes, under this mathematical identification, the past conformal boundary of the current eon. The initial singularity of our Big Bang is, in this framework, the conformally rescaled future infinity of a previous universe, not a physical event in the ordinary sense, a geometric identification, a conformal gluing of two smooth boundaries into one. This is the mathematical core of conformal cyclic cosmology, and it is important to be precise about what makes it an actual scientific theory rather than a philosophical story dressed in mathematics. The framework makes a specific physical prediction about what should be detectable in our universe, because the events of the previous eon, particularly the most energetic events, should leave imprints that survive the conformal transition, and those imprints, if they exist, should be visible in the oldest observable light in our universe. To understand what CCC predicts should be detectable, we need to think carefully about which events in the previous eon would have been energetic enough to leave lasting traces in the radiation that crossed the conformal boundary. The most energetically powerful events in any universe dominated by stars and galaxies are the mergers of supermassive black holes. When two massive galaxies collide and their central black holes spiral together into a single object, the energy released in gravitational waves in a fraction of a second can exceed the total light output of a typical galaxy over millions of years. These are the most violent events in the cosmos, not supernovas, not gamma-ray bursts, but the inspiral and merger of objects containing billions of solar masses, releasing energy that propagates outward as ripples in space-time itself. In the previous eon, these mergers happened, countless of them, over timescales that make our own cosmic history look brief. Each merger released an enormous burst of gravitational radiation, which traveled outward from the merger site, expanding as a spherical shell, gradually diluting as the universe expanded around it. Eventually, in the deep far future of that previous eon, after all the stars have gone dark and the universe has entered its black hole era, The last supermassive black holes evaporate through Hawking radiation. Their final evaporation releases concentrated bursts of predominantly electromagnetic radiation, photons that propagate outward into the dying cosmos. Now ask, what happens when the universe reaches its conformal future boundary? The radiation field, carrying within it the expanded, diluted, but geometrically encoded signatures of all the mergers and evaporations that occurred throughout the previous eon, gets compressed through the conformal identification onto the past conformal boundary of the next eon, our Big Bang. Those compressed energy concentrations, imprinted on the initial radiation field of our universe, would have expanded during the early universe into circular patches, rings of anomalously high or low temperature variance in the radiation field, approximately Gaussian in profile, with an angular diameter on the sky of roughly several degrees, or roughly about 5 times the angular diameter of the Moon as seen from Earth. This is the prediction. Penrose and his collaborators, particularly Vahe Gurzardian of the Yerevan Physics Institute, and later mathematician Christoph Meissner and physicist Daniel Ahn, call these features Hawking points. They are the fossil signatures of black holes that evaporated in the universe before ours. In 2010, Penrose and Gurzardian published a paper claiming to have found evidence of these features in the WMAP microwave background data, the precise temperature map of the sky produced by NASA's Wilkinson Microwave Anisotropy Probe. Subsequent work, published in 2018 and extended through to 2024 and 2025, examined the Planck satellite data with improved resolution and claimed to detect Hawking point signatures at statistical significance levels ranging between 3 and 5 sigma. 5 sigma, in the conventions of experimental particle physics, is the threshold for claiming a discovery. 3 sigma is evidence. If the claimed signals are genuine, and if the statistical analysis is correct, this would be direct observational evidence for a previous universe, the most significant cosmological discovery in the history of science. But here is where honest reporting requires acknowledging the full complexity of the situation, because the Hawking points claim is genuinely disputed in a way that has not been resolved. 3 independent groups of physicists reanalyzed the same CMB data using different statistical methods and found no statistically significant evidence for the concentric low variance rings or elevated temperature spots that CCC predicts. Their conclusion, published in peer-reviewed journals, was that the patterns Penrose's team identified as anomalous are consistent with what standard inflationary cosmology would produce by chance, that they fall within the expected statistical noise of a sky generated by inflation without any CCC signal present. The disagreement between these groups is not about what the data shows. Everyone agrees on the data. The disagreement is about what the data means specifically, about how to correctly calculate the probability that the observed patterns would appear by chance in the standard inflationary model. This is a statistical question, and different methodological choices lead to very different conclusions. The use of different simulation pipelines, different choices of which regions of the sky to include, different treatments of known CMB anomalies, all of these affect the outcome significantly. An August 2025 preprint from Penrose's group advanced new interpretations of existing CMB anomalies as remnants of what they call phantom black holes from previous eons, a refinement of the Hawking points concept that identifies recurring low-temperature ring patterns as inevitable CCC predictions. The analysis is ongoing. The debate has not been settled by any observation to date. The scientific status of CCC is therefore this: the theory is alive in the literature. It is generating papers and responses and refinements. It has not been falsified. It has not been confirmed. It sits in the contested space of proposals that are mathematically coherent and observationally testable, where the current data is ambiguous enough that the answer genuinely depends on methodological choices that physicists are still arguing about. The next generation of experiments may change that. The Light-Bayard satellite, a Japanese-led cosmic microwave background polarization mission, planned for launch in the late 2020s, is designed to measure the large-scale polarization structure of the microwave background with precision significantly greater than current instruments. CMBS-4, a ground-based experiment under development in the United States, targets similar sensitivity goals. The primary motivation for both is the search for primordial gravitational waves from inflation, the B-mode polarization signal that would confirm inflationary models at the quantum level. But the same data would provide the most powerful constraints yet on the Hawking points prediction, because polarization carries information about the angular distribution of energy in the early universe that temperature maps alone cannot fully reveal. If the Hawking points are present at the level Penrose's team claims, Light-Bayard and CMBS-4 should detect them. If they are absent at that level, the theory will face its most serious observational challenge yet. The answer is not yet in for conformal cyclic cosmology to work, for the heat death of our universe to function as the Big Bang of the next. A specific set of physical conditions must be satisfied, and when you list them together, the theory begins to look simultaneously beautiful and demanding. The first requirement is proton decay. If protons are stable, if they genuinely do not decay on any timescale, then ordinary matter persists in the far future as cold, inert remnants, black dwarfs, neutron star remnants, slowly diffusing atoms. These massive objects break conformal invariance and prevent the far future universe from reaching the clean, radiation-dominated state that CCC requires for the conformal boundary to be geometrically smooth. The Standard Model predicts proton stability. Every major proton decay experiment has so far found nothing. If proton decay is not real, CCC has a structural problem at its foundations that has no easy resolution. The second requirement is the eventual disappearance of mass. Even if protons decay, neutrinos appear to have small but non-zero masses. The experimental evidence for neutrino mass is now well established, even if the precise values remain uncertain. Electrons and positrons produced in the final stages of black hole evaporation have masses. Gravitons, if they have any mass at all, would break conformal invariance. For the universe to reach a truly conformally invariant state, one where the conformal boundary is exactly smooth rather than approximately smooth, all massive particles need to ultimately have their masses go to zero. The mechanism Penrose has proposed for this is the gradual relaxation of the Higgs field back toward its symmetric state over cosmological timescales. The Higgs mechanism, confirmed by the detection of the Higgs boson at the Large Hadron Collider in 2012, is what gives elementary particles their masses. Particles acquire mass through their interaction with the Higgs field, which pervades all of space. In the extreme early universe, above a certain temperature, the Higgs field was in its symmetric phase, and particles had no mass. As the universe cooled, the Higgs field underwent a phase transition into its current configuration, breaking the symmetry and giving particles their masses. Penrose speculates that in the extreme far future, after all, the black holes have evaporated. After the universe has been expanding for timescales that make a googol of years look brief, the Higgs field might gradually relax back toward its symmetric configuration. The mechanism is not specified in the Standard Model. The Standard Model does not predict this. It is physical speculation motivated by the requirements of the theory, connected to real open questions about the long-term behavior of the Higgs vacuum, but not derivable from any currently confirmed physics. The current Higgs field sits in what physicists call a metastable vacuum, not the true lowest energy state, but a very stable local minimum. Running the standard model equations forward to high energies suggests that the universe may be in a false vacuum, stable for cosmic timescales, but not necessarily eternally so. Whether the Higgs vacuum is absolutely stable, metastable, or genuinely unstable has implications for the deep future of the universe that are not yet resolved. The third requirement involves the question of information preservation in black hole evaporation. Hawking's original calculations described Hawking radiation as perfectly thermal, carrying no information about what fell into the black hole. Under this interpretation, information is destroyed when matter falls into a black hole, which is in direct tension with the fundamental requirement of quantum mechanics that physical evolution preserve information. Almost all modern theoretical work on black holes, informed by insights from string theory and the ADS-CFT correspondence, strongly suggests that information is in fact preserved, that Hawking radiation is subtly non-thermal in a way that encodes the quantum state of everything that fell in, even though that information is so scrambled as to be practically unreadable. If information is preserved, if unitarity holds as the mainstream now suspects, then the radiation that fills the far future universe is not a featureless thermal bath. It is a fantastically scrambled but complete encoding of the entire history of the previous eon. Whether this information-laden radiation can still produce a geometrically smooth conformal boundary, whether the presence of all that scrambled information is compatible with the conformal smoothness that CCC requires, is an open technical question that sits at the intersection of quantum mechanics and general relativity. Precisely the regime where we do not yet have a fully consistent theoretical framework. The fourth requirement is a stable positive cosmological constant, the energy of the vacuum, dark energy, driving the eternal accelerated expansion of the universe. The conformal structure of CCC, particularly the properties that make the future conformal boundary a space-like surface that can be smoothly identified with the past conformal boundary of the next eon, depends on the universe expanding into a de Sitter-like geometry. If dark energy is not constant, if it decreases over time, or changes sign, and eventually causes the universe to stop expanding and recollapse, then the conformal structure changes in ways that break the CCC framework. Recent observational data from the Dark Energy Spectroscopic Instrument, released in 2024 and 2025, has shown hints that dark energy may be evolving, that it may not be a pure cosmological constant but a dynamical field that changes with time. If those hints harden into confirmed evidence as the survey accumulates more data, they would create significant tension with the key assumption of CCC. The jury on this is still genuinely out. For requirements, each one either uncertain, contested, or dependent on physics beyond what we have confirmed. Any one of them could independently fail, and if any one fails, the framework does not work in its current form. Taken together, they paint a picture of a theory that is internally coherent and geometrically elegant, but that is making specific demands of the universe that the universe has not yet agreed to satisfy. Penrose acknowledges all of this. The elegance of the conformal geometry is, in his view, evidence that the framework is pointing at something real. His critics, and there are serious credentialed critics, argue that elegance is not evidence, and that a theory requiring for separate unconfirmed physical conditions to function is doing a great deal of work with very little observational scaffolding. Both positions are defensible. The theory is not proven. The theory is not dead. Conformal cyclic cosmology is not the only physically motivated alternative to heat death. It is worth mapping the landscape of possibilities, not to be exhaustive, but to understand what distinguishes CCC from its competitors and why it occupies a unique position among them. The Big Rip is the most dramatic alternative ending. In the standard cosmological picture, dark energy has a fixed energy density described by the cosmological constant. It does not change as the universe expands. But if dark energy is instead a dynamical field with a specific type of energy equation, one in which the energy density actually increases, as the universe expands, then the consequences are extreme. An increasing dark energy density drives increasingly rapid expansion, and eventually the expansion becomes so fast that it tears apart gravitationally bound structures. First galaxy clusters are ripped apart, then galaxies, then solar systems, then individual planets, then atoms, and finally space-time itself dissolves in a singularity of infinite expansion rate. This Big Rip, if it occurs, would end the universe in a finite time. Estimates of when, depending on the specific dark energy model, put it anywhere from 20 billion to several hundred billion years from now. The Big Rip does not produce a smooth conformal boundary. It produces a genuine singularity of a type that is incompatible with the CCC framework. If the universe ends in a Big Rip, CCC has no mechanism to operate. Vacuum decay is another possibility that standard physics takes seriously, and that depends only on the already established physics of the Higgs field. The Higgs field appears to sit in a metastable minimum, a stable local minimum of the Higgs potential, but potentially not the absolute minimum. A quantum tunneling event could, in principle, nucleate a bubble of true vacuum somewhere in the universe. This bubble would expand outward at the speed of light in all directions, converting everything it passed through to a region where the laws of physics are slightly different. Different particle masses, different interaction strengths. There would be no warning, no gradual process, just an expanding wall of altered physics arriving at the speed of light. The estimated timescale for spontaneous vacuum decay in the current universe, based on measurements of the Higgs boson mass and the top quark mass, is astronomically large, far longer than the current age of the universe, and likely longer than the stelliferous era, but it is not infinite. If vacuum decay occurs before the universe reaches its heat death, it would preempt the entire CCC scenario. The universe would not arrive at the conformally invariant radiation-dominated state. It would end in the expansion of a true vacuum bubble, whose consequences we cannot fully predict. Loop quantum cosmology proposes that quantum gravity effects at the Planck scale, the scale of the smallest physically meaningful length, where general relativity and quantum mechanics are both relevant, prevent the formation of singularities. In this framework, what we called the Big Bang was not a singular beginning but a big bounce. The universe contracted from a previous phase, reached a minimum density at the Planck scale, and then began re-expanding. The contracting phase before the bounce was a previous universe in this picture, and the current expanding phase is its continuation. This is genuinely cyclic, but the mechanism is entirely different from CCC. It requires quantum gravity physics that we do not yet have a complete theory of, and it does not address the entropy problem in the same way. CCC attempts to eternal inflation, associated primarily with the work of physicists Andre Linde and Alan Guth, proposes that the inflationary process that drove the extreme expansion of the very early universe never fully ended on the largest scales. While inflation ended in our local region, producing the smooth, flat universe we observe, quantum fluctuations in the inflation field keep inflation going eternally. In other regions of a much larger space, constantly, new bubble universes nucleate in this eternal inflationary background, each one expanding into a potentially habitable cosmos. Our universe is one of an infinite number of such bubbles. This is cyclic in a different sense. There is always another universe being born somewhere, but it shares no conformal geometric structure with CCC, and it does not explain the low-entropy initial conditions of any particular bubble. It merely posits that all possible initial conditions are realized somewhere, and we necessarily find ourselves in a bubble compatible with our existence. What distinguishes CCC from all of these is that it is the only theory that directly attempts to solve the initial conditions problem, to explain why the Big Bang started in a 1-in-10-10-2- the -power- of -10-2- the -power- of -100-100-100-100-20-3 configuration through a concrete geometric mechanism. The other theories either ignore the problem, sidestep it, or address it through mechanisms that Penrose argues fail to account for the full scope of the thermodynamic fine-tuning. CCC is the only framework that says the extraordinarily special initial conditions of our Big Bang are not a coincidence or an anthropic selection or an arbitrary input. They are the output of the geometry of the previous eon's ending. That is a more ambitious claim than any of the alternatives. It is also a more specific and more testable claim. And in science, a theory that makes specific, testable predictions, even if it is ultimately wrong, is more valuable than a theory that makes no predictions at all. Here is a question worth asking, even if the answer turns out to be disappointing. If conformal cyclic cosmology is correct, and if each eon leaves imprints on the next through the conformal boundary, could a sufficiently advanced civilization in the previous eon have deliberately encoded a message in those imprints? Could whatever intelligence might have existed in the universe before ours have understood the mathematics of the conformal transition and attempted to leave information for whatever came next? The answer, in practice, is almost certainly no. But working through why illuminates something genuinely important about the nature of information, the structure of the conformal boundary, and the physical constraints on any civilization, no matter how advanced. Start with what actually crosses the conformal boundary. The information that survives the transition from one eon to the next is carried in the radiation field in the detailed quantum correlations among the photons, gravitons, and other massless particles that make up the radiation bath of the far future universe. In principle, this is extraordinarily rich. Every photon carries phase and polarization information. The correlations among all the photons in the radiation field encode, in principle, the entire quantum history of the eon. Every particle interaction, every stellar evolution, every black hole formation and evaporation, going back to the eon's own Big Bang. But here is where the engineering problem begins to reveal its true scale. By the time a universe reaches its conformal future boundary, the radiation has been expanding and redshifting for timescales of roughly 10 to the power of 100 years. That is a googol of years. The current age of our universe is approximately 10 to the power of 10 years. The ratio of these timescales, 10 to the power of 90, is itself incomprehensibly large. Over that duration, the wavelengths of photons have been stretched by expansion factors that make the entire expansion of the observable universe since our own Big Bang look infinitesimal by comparison. The energy of each individual photon approaches zero, not low, not faint, effectively zero, and the quantum correlations that encode information, the subtle entanglements between photons that carry the history, of the eon are spread across spatial scales that make the observable universe today look like a single atom compared to the distances involved. The information is there. Quantum mechanics requires it to be, but it is distributed across spatial scales and encoded in correlations of such extraordinary delicacy that accessing any meaningful portion of it would require a measurement process that is physically impossible by any standard we can articulate or imagine. Now ask what it would take to deliberately encode a message into that radiation field. Not just leave an accidental imprint, but actually structure the quantum state of the radiation in a way that produces a detectable, decodable signal in the next eon's early universe. You would need to coherently manipulate the radiation field across scales, spanning the entire observable universe of your eon, not just your galaxy, not your galaxy cluster, the entire observable universe, hundreds of billions of light-years across. You would need to coordinate the quantum states of photons separated by billions of light-years from each other, imposing specific phase relationships and polarization correlations across distances that light itself could barely connect in the entire age of your universe. You would need to do this with quantum mechanical precision, on timescales when the available energy gradients have been reduced to essentially nothing near the end of your eon's life. This puts the task somewhere beyond what the Kardashev scale was designed to describe. A Kardashev Type 3 civilization harnesses the energy output of an entire galaxy, something on the order of 10 to the power of 44 watts continuously. That is an enormous amount of power by any standard. But the scales required for cross-eon communication are roughly 9 orders of magnitude, larger than what even a Type 3 civilization can access. The task requires not a galactic civilization, but something like a civilization coordinating coherent quantum operations across the entire observable universe, under the thermodynamic constraints of a dying cosmos, where almost no usable energy remains. And even if such a thing were somehow achieved, the signal would be compressed through the conformal transition into an imprint, so faint and so scrambled by subsequent cosmic expansion that distinguishing it from the natural statistical structure of the radiation bath would require the receiving civilization, our civilization, to have already solved the very measurement problems that make reading quantum correlations in the far future radiation essentially impossible. So the honest answer is this: no. A previous civilization almost certainly could not have left a deliberate message, not because the physics forbids it in principle. The physics is agnostic about extreme enough hypothetical feats of engineering, but because the gap between what any physically realizable civilization could do and what the task actually requires is not a gap of degree, it is a gap of kind. The difference between building a very tall building and building a structure that reaches the moon with your bare hands, what does cross the boundary, and what we might actually be able to detect, is something more humble and more interesting. The unintentional imprints, the gravitational wave signatures of supermassive black hole mergers that propagated through the previous eon's spacetime, eventually reaching the conformal future boundary and leaving their geometric traces compressed into the radiation of the next eon's early universe. The statistical signatures of large-scale structure, the way matter organized itself on the largest scales in the previous cosmos, reflected faintly in the temperature fluctuations of our own microwave background. These signals were not sent. Nobody addressed them to us. Nobody knew we would be here to receive them. They are fossils, the footprint left in concrete that had not yet set, not deliberately, not intentionally, simply because something heavy was there at the right moment. And fossils, as any paleontologist will tell you, can tell you an enormous amount about what came before, about the scale of the creatures that walked. the environment they inhabited, the events that shaped their world, if you know how to read them. The entire discipline of paleontology is the science of extracting history from unintentional records. That is exactly what Penrose and his collaborators are attempting when they analyze the microwave background for Hawking points. They are not listening for a message. They are reading a fossil record. Stop for a moment and think about the physical space you are actually occupying right now, not in the abstract. The literal volume of air around your body, wherever you happen to be. That space is not empty. It is one of the most densely populated environments in the universe in terms of the sheer variety of electromagnetic radiation passing through it simultaneously. And most people move through it their entire lives without registering any of it, because the instruments for detecting it are not built into the human body. Visible light is here bouncing off surfaces, entering your eyes, carrying information about shape and color and the spatial arrangement of everything you can see. But visible light is an extraordinarily narrow band of the electromagnetic spectrum, a thin slice of frequencies that the human visual system evolved. Sensitivity too, because they are the frequencies the sun outputs most abundantly and the atmosphere transmits most cleanly. Outside that narrow band, in every direction, the room is equally full of information you cannot sense. Radio waves are passing through your walls right now, many of them carrying encoded signals from broadcast towers and cell towers and satellites in orbit. The walls of most buildings are essentially transparent to most radio frequencies. The signals from stations broadcasting hundreds of kilometers away are in this room at this moment. You are, without any awareness of it, sitting inside a radio receiver that you cannot tune. Microwaves from your local wireless network are bouncing between router and device, filling the room with a structured electromagnetic field. Infrared radiation from every warm object nearby, your own body included, is propagating continuously in all directions, absorbed and re-emitted by the walls and surfaces around you. Ultraviolet from any sunlight that reaches inside, X-rays from cosmic sources filtering through the building, gamma rays from trace radioactive decay in the ground and the materials around you, neutrinos from the sun, passing through your body in their billions every second, interacting with almost nothing. The room is not quiet, it is extraordinarily busy, and you move through all of it unaware, because you have instruments for only one narrow frequency band, and those instruments are mounted in your skull. But all of that, every radio wave, every infrared photon, every cellular signal, every cosmic ray, every solar neutrino, is local. It was generated nearby, or recently, or both. Those signals are young. They carry information about the present state of the world around you. What is not local, what is not recent, what is in an entirely different category from everything else filling this room, is the cosmic microwave background. The cosmic microwave background is not a distant wall of light sitting at some remote edge of the observable universe. That is a common misunderstanding, and correcting it makes what follows feel considerably more immediate. The CMB is here in this room, right now, filling the space around you. Microwave photons from the cosmic background are passing through your body, at this moment, at a rate of hundreds of millions per cubic centimeter per second. They are not arriving from one direction, they are arriving from every direction simultaneously, with almost perfect uniformity, because they fill the entire universe homogeneously. Every cubic centimeter of space anywhere in the observable universe contains the same bath of CMB photons that exists in your room. These photons began their journey approximately 380,000 years after the Big Bang, the moment the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time in cosmic history. Before that moment, the universe was opaque to light. The plasma of charged particles scattered photons so rapidly that light could not travel any significant distance. After that moment, called recombination, the photons that existed at the transition streamed outward in all directions, and they have been traveling ever since, for nearly 14 billion years without interacting with anything that significantly altered their state. The temperature variations encoded in the CMB, the tiny hot and cold spots, the ripples of 1 part in 100,000, are the direct, unprocessed imprint of conditions at that transition moment. The density fluctuations in the primordial plasma, the acoustic waves that had been propagating through the universe for 380,000 years, the gravitational effects of the initial distribution of dark matter. The CMB is, in a precise sense, the oldest photograph we can ever take of the universe. No telescope, no instrument, no observation of distant galaxies or ancient quasars comes anywhere close to looking back as far as the CMB. When we observe galaxies with the James Webb Space Telescope from several 100 million years after the Big Bang, we are looking at a universe that had already had hundreds of millions of years to form structure. The CMB shows us the universe as it was 380,000 years in the surface of last scattering. The first image the universe was transparent enough to produce, and it is here, in your room, passing through you, at this moment. Now add Penrose's interpretation, because if conformal cyclic cosmology is correct, then the age we just assign to those photons is not their full age. 380,000 years after our Big Bang is when they were last scattered, when they decoupled from matter and became free to travel. But the energy that produced them, the radiation field they are part of, did not originate at our Big Bang. It crossed through the conformal boundary from the previous eon. It is, in Penrose's framework, radiation that predates our universe entirely. Radiation whose energy, diluted by many factors of 10 but still present, was already in existence in a universe that had been expanding for far longer than ours has been alive, and the temperature fluctuations encoded in that radiation, those tiny variations of 1 part in 100,000 that the Planck satellite, mapped with such extraordinary precision, contain, compressed within them, if CCC is correct, the afterglow of events that happened in the universe before ours. Supermassive black holes merging in a cosmos that burned and died before our Big Bang. Their gravitational energy traveling outward, reaching the conformal boundary of that previous eon, crossing through the transition, and imprinting itself as circular patterns in the radiation of our early universe. The photons in your room may be carrying postal marks from a previous cosmos. Now, the honesty part, because this is important, and it would be wrong to pass by it. This is not confirmed. The Hawking point signals that Penrose and his collaborators claim to have found in the CMB data are disputed by other physicists using different statistical methods. The question of whether those circular patterns are genuinely anomalous, genuinely inconsistent with what standard inflationary cosmology predicts, or whether they are simply what you would expect to find if you look hard enough at any sufficiently large dataset, has not been definitively resolved. Analyzers using machine learning techniques on high-resolution CMB data have generally found that the claimed features are consistent with the standard model's predictions without any CCC signal required. The mainstream cosmological community is at best skeptical and, more accurately, largely unconvinced. There is a real possibility, perhaps even a likelihood, by the weight of current opinion, that the CMB fluctuations passing through your room are exactly what standard inflation produces: random quantum fluctuations from the inflationary epoch, imprinted on the primordial plasma, extraordinarily interesting in their own right. rich with information about the first fractions of a second of our universe, but carrying nothing from before our Big Bang, because there was no before our Big Bang in any physically meaningful sense. But there is also a possibility that they are not, and the reason that possibility deserves attention rather than dismissal has nothing to do with Penrose's reputation or the elegance of his mathematics, because neither of those things is evidence. The reason is structural. CCC makes a specific, quantitative, testable prediction about patterns in a real data set that already exists and can be analyzed. It is not a vague claim about the universe being cyclic in some philosophical sense. It is a claim that says, look at the CMB data. Look for circular rings of anomalous temperature variance at specific angular scales. You should find more of them, and stronger ones, than the standard model predicts. That is the kind of prediction that science can engage with. It is falsifiable. It is being tested. The answer is not yet in. Let us end at the boundary itself, because that is where everything converges. Imagine you could somehow be present at the conformal future boundary of a dying universe, not from outside it, because there is no outside. Outside requires space, and space requires a reference scale, and reference scales require mass, and mass is gone, not from a distant vantage point, because distance requires the same infrastructure of mass and clocks that has ceased to exist at this boundary. Imagine instead that you could be present at the geometric surface that represents the endpoint of all structure, the place where time and scale and distance lose their physical meaning entirely, and the universe arrives after an incomprehensible duration at the only state it was always moving toward. On one side of this surface is the infinite future of a universe that has been running for a duration so large that the number describing it has more digits than there are particles in the observable universe, a universe that spent its first few billion years forming galaxies, its next 100 trillion years burning through stellar fuel, its next stretch of time longer than that, slowly dissolving its matter through proton decay, its next stretch longer still, converting every last black hole into a final burst of Hawking radiation, and then cooling, expanding, redshifting, until the last photon's energy dropped to effectively zero, and the universe arrived at its final, maximally disordered, featureless state. All of that history, every star that ever burned, every planet that formed, every civilization that arose and eventually ended, every black hole that consumed matter and slowly returned it to the universe as radiation is encoded somewhere in the quantum state of the radiation field that ends at this surface, not lost, not erased, encoded in correlations so complex, so dilute, so spread across spatial scales, so enormous that no physical process inside the universe could ever decode them. A complete record that nobody can read. On the other side of the surface, in Penrose's framework, is the beginning of the next eon. Not beginning in the sense of starting from nothing, beginning in the sense of continuing. The conformal geometry of the previous eon's future boundary becomes, through the mathematical identification at the heart of CCC, the initial condition of the new universe. The Weyl curvature at the boundary is forced to zero by the geometric smoothness of the matching surface, and zero Weyl curvature is precisely the extraordinarily special initial condition that produces a low-entropy beginning. The kind of beginning that allows a thermodynamic arrow of time to exist, that allows structure to form, that allows stars and galaxies and planets and eventually life to emerge. The apparent fine-tuning of the Big Bang, that 1-in-10-2- the dash power dash of dash 10-2-10-2- the dash power dash of dash 1-100-100-20-3 probability is not a coincidence in this framework. It is not an anthropic accident. It is not selected from some external menu of possible initial configurations by some unspecified process. It is a geometric constraint. The conformal boundary has only one allowed curvature. The new universe has only one allowed starting geometry. The improbable ordering is forced. This is the central claim of conformal cyclic cosmology, and it deserves to be appreciated for what it is attempting before any judgment about whether it is correct. The deepest problem in cosmology, why did the universe begin in a state of such extraordinary, almost impossible order, is answered not by appealing to luck, not by postulating a multiverse that samples all possible starting conditions, not by invoking a principle that says observers necessarily find themselves in universes with properties compatible with observation. It is answered geometrically. The universe began ordered because the object it was born from was conformally flat at the boundary. Conformal flatness at the boundary means zero Weyl curvature. Zero Weyl curvature means low gravitational entropy. Low gravitational entropy means a thermodynamic arrow of time. A thermodynamic arrow of time means structure conform, and structure forming eventually means, here we are, having this conversation. The chain extends infinitely in both directions. There was a universe before ours. There was a universe before that. There was a universe before that, going back eon by eon, with no first eon, no original universe, no moment at which the chain started from nothing. Each eon begins in the low entropy state that the conformal transition forces, builds its structure, burns its fuel, evaporates its black holes, reaches its conformally invariant ending, and hands off. Each eon is complete in itself, a full universe, from Big Bang to heat death, and each eon is one step in a process that has no beginning and no end, a relay that has always been running and will always run, in which no single runner is the first or the last. There is no creation event in this picture. There is no moment at which something came from nothing. There is only the endless conformal handoff, universe to universe, each one dying into the beginning of the next, each death as quiet and geometrically inevitable as the one before it. You should hold all of this with appropriate epistemic humility, and Penrose himself would insist on this more than anyone. CCC requires proton decay, which decades of dedicated experimental searching have not found. It requires particle masses to eventually reach zero through a mechanism the Standard Model does not predict, and which has no confirmed physical description. It requires a specific relationship between information preservation in black hole evaporation and conformal boundary smoothness that has not been fully worked out, and which sits in tension with mainstream understandings of quantum mechanics. Its primary observational prediction, the Hawking points, remains disputed by groups of physicists who find no statistically anomalous signal when they apply what they consider more rigorous statistical methods. None of this is settled. All of it is contested. The geometric core of the theory, the conformal compactification, the boundary identification, the mathematical mechanism of the handoff, is built on well-established differential geometry that the physics community has used for decades. The physical requirements attached to that geometry are the contested part. Whether the universe actually satisfies those requirements is exactly the question that experiments over the next decade are positioned to test. Light-Bayard, CMBS-4. Better measurements of the proton lifetime from upgraded underground detectors. Better measurements of the Higgs vacuum stability from future particle physics experiments. Better constraints on the evolution of dark energy from large-scale structure surveys. All of these will provide data that either supports, constrains, or potentially falsifies key components of the CCC framework. The theory is making contact with experiment. The results are not yet conclusive, and yet the question refuses to go away, regardless of whether CCC survives experimental scrutiny. The question of why the Big Bang started the way it did. The question of what, if anything, preceded the Big Bang. The question of whether heat death is a termination or a transition. These questions do not have satisfying answers in the standard cosmological framework, and they are not going away simply because the mainstream has not embraced Penrose's proposed solution. CCC offers an answer. It may not be the right answer, but it is a real answer in the precise sense that matters in science. It is mathematically specific, physically grounded, and empirically constrained, even if every component of it is eventually falsified. The framework will have transformed the initial conditions problem from a vague philosophical discomfort into a specific geometric question with a specific geometric answer that can be tested and, if wrong, ruled out. That is not nothing. In the history of physics, the theories that asked the right question precisely enough, even when they ultimately got the answer wrong in detail, have repeatedly been the ones that pointed the way to something deeper. The radiation in your room right now is, at minimum, the oldest observable thing in our universe. 13.8 billion years of uninterrupted travel, carrying the direct imprint of conditions 380,000 years after our Big Bang, unmodified by anything that happened in between. Whether it carries anything older than that, whether buried in the temperature fluctuations of the cosmic microwave background, there are circular whispers of black holes that evaporated in a universe that preceded ours, is a question that is, at this moment, genuinely unanswered. The universe may not end in silence. It may end in a handoff, clean, geometric, inevitable, the way a flame passes from one candle to the next, not the same flame, not a copy, a continuation, made possible by the geometry of the transfer, requiring no mechanism beyond the mathematics of the boundary itself. And somewhere in the unimaginable future of our universe, long after the last star has gone dark, long after the last black hole has completed its slow evaporation, long after the last photon has redshifted to an energy that is for all purposes zero, a conformal surface is forming, quietly, inevitably, the boundary between our story and the next one, the ending that functions as a beginning, the death that is, from the other side of the geometry, a birth. Roger Penrose may be wrong about the details. He is almost certainly right about the question. And in physics, as in most things that matter, asking the right question precisely enough is more than half the work. The rest is waiting for the data.